Related rates problems measure the instantaneous rate of change of something given the instantaneous rate of change of something else. In related rates problems, we find the rate of change of something given the rate of change of another thing. Because rate of change is usually not constant, we most likely will have to relate to a specific instant, which will be given by a specific time or by what occurs at this specific instant. Here is our first example. Through this example, I'm going to show you what to do, more or less, because this is a very simple one. Let y equals x to the power 3 plus 4x. Find the rate of change of y when x equals 2 units and dx dt equals 3 units per second. Both x and y are functions of the time, so x is actually x of t and y is actually y of t. We have to view all these problems as an ongoing process that really continues forever and never stops. Let's see what is written here that is always true. It's definitely only the connection between y and x. Why it's not true to say that x equals 2 and dx dt is 3 units per second always true? Because if you read it says, find the rate of change of y when. It means that there is ongoing change, and when x equals 2 and dx dt equals 3 units per second, it actually happens only in a very short instant of time. So the only thing that is always true is the connection between y and x. But if this is true and we have an equation here, we can differentiate both sides with respect to t. The real variable here is t. So we have to use a little chain rule because y is a function of t and x is a function of t. When we differentiate y with respect to t, we get dy dt. X to the power of 3, using the chain rule, 3x to the power of 2, but then we have to differentiate the inner function x, and we get dx dt. So we get here 3x to the power of 2 dx dt. And then we have to differentiate 4x, and we get 4 times, and the derivative of the inner function x is dx dt. Please pay attention. Y prime is going to be dy dx because y is a function of x. It is totally meaningless in related rates problem. In related rates problem, we will have to use only the Leibniz notation, and everything is going to be d something dt. Now we have to focus on the snapshot. What is this snapshot? There is an ongoing process, but we need to find some information, in this case, the rate of change, at a very specific instant. This instant can be given by time, very specific time, but also it can be given like here by something that happens at this specific time. In this case, it is when x equals 2 and dx equals 3 units per second. When we take snapshot, like in real life, we are freezing only the instant that we'd like to inspect. When we are finishing taking this picture, the picture is already not the same. If you're taking a picture of the crowds doesn't stop, doesn't freeze, but in your snapshot, it is an instant that is frozen. So in the snapshot, we would like to see what to substitute in the dy dt equals 3x to the power of 2 dx dt plus 4 dx dt. We see that x equals 2, and we see that dx dt equals 3 units per second. This is for the x, this is for dx dt, and this is dx dt. And we just calculate the number and we get 48. In this case, the units of the answer, dy dt, is units per second. dy dt equals 48 units per second. Here is another problem. At a certain time, the width of a rectangle is 5 centimeter and increasing at the rate of 0.2 centimeter per second, and its length is 10 centimeter and decreasing at the rate of 0.3 centimeter per second. How fast is the area of the rectangle changing at that time? Is it increasing or decreasing? This problem is a little bit more complicated than before. This problem also does not have any function, so we have to find a function. But it is very clear that this is about an area of a rectangle that has width and length. And that's why we say that A equals W times L. Obviously, if W is a function of t and L is a function of t, then also A is a function of t. And this is always true. Now we're going to differentiate. Pay attention. It doesn't matter that we have A, W, and L. It means 3 variables because everything has to be differentiated with respect to t. So we don't care to have many variables now. So let's differentiate. We're differentiating A with respect to t and we get dA dt. Then we have W and L, so we have to use the product rule. Differentiate the first with respect to t, we get dW dt times the second times L, plus differentiate the second, which is L, we get dL dt times the first, and we get W. So we get the dA dt equals dW dt times L plus dL dt times W. This is the only thing that is always true. If you look what it's written in the problem here, at a certain time, and all the numbers that you see here are related to this certain time at which we have to find the related rate of A with respect to the change in W and L. So now we have to focus on the snapshot. Let's see what it's written here in the problem. What do we have to substitute? The width of the rectangle is 5 centimeters, which means that W is 5 centimeters. And increasing at the rate of 0.2 centimeter per second. It means that dW dt equals 0.2 centimeter per second. The length is 10 centimeters, so L is 10 centimeters. And decreasing at the rate of 0.3 centimeter, which means decreasing that it is minus 0.3 centimeter per second. We are substituting for dW dt. We are substituting for L. This is for dL dt. And this is for W. And then we calculate the number. Okay, we get 2 minus 1.5 and you get 0.5. And the answer is the area is increasing at the rate of 0.5 square centimeters per second. How to recognize related rate problems? We did 3 problems, and let's see how to recognize. In this one, find the rate of change. In this one, how fast does? The more problematic part is how to recognize the snapshot. When x equals 2 units and dx dt equals 3 units per second. In this one, when the radius is 10 centimeter. And in this one, at a certain time.